I have some background sound coming in. If you guys could mute your phone, unless you want to say something for now, because I'm getting an echo here. Okay, very good. All right, good evening, everyone. Celso Batalha, Evergreen Valley College. This is Astro 10. And when you open the course, this is what you have. If you go on modules or take this link, and then you scroll down to the chapter of the week we are considering, and we are in chapter 2. So what I will do today and in following weeks is to focus on the simulations, Nebraska simulations, as well as to discuss some of the materials that are going on in our course. So since I haven't lectured anything yet, and since today is technically my first interaction with all of you, and this is being taped, I would like to spend some time to talk about the main point of chapter 2, which is to introduce the main types of motions that we experience in our everyday life. Not only in the 24 hours of a day, but also in a weekly basis and in a monthly basis. We see that there is a progression of seasons. We all know about it. But also, if you observe the sky, you know the sky goes through some changes during the weeks that follow one another. So why these changes occur and why are we studying them in chapter 2? So let me show you a planetarium software that is not so much different from Stellarium that we are going to work in the future. So here we have September 11, 2017 at 7:19 at certain hours, San Jose. So this is the sky as we have in San Jose. So if you go outside and look out towards the south direction, so this S stands for south, this is the type of sky you see. There will be something bright in the sky. If you have good eyes, you might be able to see it. It's right there, it's barely visible. And if you look to your left-hand side, you're going to probe the eastern sky. E for eastern sky. And if you look to your right-hand side, that's going to be your western sky. And there is something bright over there, and that is Jupiter. So Jupiter is really going down. It's a planet, it's going down. And above Jupiter, we have some other issues that you can see. So this is a planetary, it's not a real sky. I don't have a camera pointing to the sky. But what you notice is that time is ticking. Look at that. Every second, a second has passed. And but we don't think the sky is moving, apparently moving, just by staring at it. But what I'm going to do, since this is a software, I will speed up the flow of time. And now you can see that time is flowing quickly, right? And slowly you see the night sky appearing. Now it's getting dark. And slowly the sky moves from the eastern part of the sky. And the process by which stars go from below horizon to above horizon, this process is called rising of stars. So star rise is a process by which the star goes from below horizon to above horizon. And if you look towards the western sky, W is for western sky, now the sky is setting in that region. So the stars are going from above horizon to below horizon. So Corona Borealis, this asterism here, is now setting. And if you look due south, what you perceive is the following. So the stars, they rise in the east, and then it slowly progress and hit maximum height when they cross due south, and then they set in the western sky. So why the sky seems to be moving, apparently moving, from the eastern part of the sky in our left-hand side if we are facing south to the western sky in our right-hand side. So why the sky seems to be moving that way? And if you wake up at 4:30 a.m., you're going to see Orion slowly progress in the sky and reaching maximum height at about 6 o'clock or so. And a new day is coming by. Now the sun is coming and all the stars are washed out because the sun is too bright. And then we don't see stars anymore. So why is it the stars appear to rise in the eastern sky and set in the western sky? So 2,000 years ago or more, and here's the moon over there. See the moon there? That's the moon now. The moon is setting down. The moon is going down. So 2,000 years ago or more, Greek philosophers, they came up with this idea of a celestial sphere. So it appears, and if I can get rid of daylight, there you go, there is no more daylight, right? The sun is there. So these Greek philosophers, they thought, okay, if the stars are dots, or they are holes, or they are points of light, or if they are God, whatever interpretation they gave, and if the stars happen to be glued to the celestial sphere, what we see is the celestial sphere going from east to west on a daily basis. And then it was very easy for them to consider that Earth was in the center of the universe and the stars were in celestial sphere rotating from east to west on an hourly basis. So the notion of celestial sphere is a notion of something that really does not exist. But it helped these ancient philosophers to explain this type of motion because quite simply they could go outside. There was no TV in those days, no light pollution as we have nowadays, and they could mark position of stars in the sky in tablets in a given time. And then they could go back to the same spot and look to the sky again 2-3 hours later and see that the entire skies had moved. So what is the reason for that? So that's what we study in astronomy nowadays. So this apparent motion, which is called daily or diurnal motion, is caused not by a celestial sphere with the stars dragging and moving from east to west, but it's caused by Earth itself rotating in space, spinning in the space from the western part of the sky to the eastern part of the sky. So in reality, if you think the stars are not moving, in fact they are, but they are so far away that to detect their motion, you need to use highly advanced technology. So the stars are so far away that we cannot visually detect their apparent motion. So for all purposes, the stars are immovable. So, but if you conceive that you happen to be sitting on an Earth that is spinning from your right-hand side to the left-hand side, then you can explain the so-called daily or diurnal motion. Does that make sense? So daily or diurnal motion, this apparent motion of stars from the east to west, is caused by Earth itself rotating or spinning in space from the western part of the sky to the eastern part of the sky. So Earth has an eastward motion, if you will. Now that is explain the days and nights, and I could speed up this motion, right? And I could make a little bit more dramatic. There you go. And even with daylight, it will appear much more dramatic. Now the sun is coming, and the sun rises in the eastern sky, and the moon is setting over there, and then a few hours later, the sun is going down. Why is that? Not because the sun goes around or revolves around Earth. Earth itself is spinning on its axis of rotation from the western part of the sky to the eastern part of the sky. Now, let me stop here and now bring you to the second type of motion, which is called Earth revolution around the sun. So there are three major types of motion. One is Earth spinning on its axis, and the other one is Earth revolving around the sun. In fact, Earth does the two things at the same time. It spins on its axis and then goes around the sun. So if I could represent Earth rotating on its axis like this, and this part of my hand is the sun, Earth goes like this and then orbits the sun. Oops, that's a very bad representation, but I hope you got it. So in order to visualize that, what I'm going to do, I'm going to get rid of daylight. Orion is up there in the sky, and Taurus is right there. Let me bring the constellations of Zodiac. Constellations of Zodiac with their labels. So now we have Taurus in the sky, Aries over there, Gemini, Moon is in Gemini, and Cancer. And let me bring their labels. Okay. And more so, let me bring a line that is so-called ecliptic line. Let me see if I can get it. Show clip. There you go. So what ecliptic line is? Ecliptic line, this green line over here, is a line defined by the motion, the apparent motion of the sun across certain constellations, which are called constellations of Zodiac, and you might have heard about it. And the sun apparently does this path in a yearly basis. So during the year, the sun goes through the 12 constellations of Zodiac, and in fact, astronomers introduce a new constellation called Ophiuchus. And in the Zodiac, now we consider 13 constellations in the Zodiac. So the sun apparently moved through these constellations more or less every month. In a month, it's going to be in a different constellation. So in order to visualize this apparent motion, what I would like us to imagine is that we get rid of daylight, so we can see the stars during daylight, but more so, we keep staring at the same sky region all the time. In other words, imagine the camera of my computer is the sky region that I'm facing, and I'm Earth, I'm planet Earth. So I'm facing this sky region, I'm facing you now, and then in 24 hours, I realize I do this spinning, right? I go around my axis of rotation, and then I'm back looking at the same region. So imagine that I open my eyes and I see this region in the sky, and then I close my eyes and I spin and I don't see anything else. And then about 24 hours later, it's not exactly 24, I open my eyes and then I see the same sky region. So what I'm doing in this simulation is imagine that you're going out of Earth and then you're staring at the same sky region all the time, and you keep track of what's going on in that sky region, ignoring Earth rotation below you. So it's a way to say, okay, if Earth does not rotate, and if Earth keeps going around the sun, what would I see if I keep staring at the same region all the time? So let's see what happens if we do that. So let's change to our time frame like this. Oops. So now we are in October 11, 2017, and it's 2:38 p.m. And I have one sidereal day. There you go. So let me go one step, another day, another day, another day. So you might be thinking, why the stars are not moving from east to west? Well, they are not moving from east to west because imagine I'm staring at the same region all the time and I'm not moving along with Earth in its spinning process. I'm not spinning with Earth. I'm staring at the same region all the time. And as I do that, and let me bring labels to the planets. And as I do that, I don't know that this should be here. I observe that planets in general, and the moon and the sun always, they move in a direction towards east. They have an eastward motion. Look at Venus. Venus is going eastward. The moon is going eastward. Jupiter is also going eastward as well as Mars. Mercury in the left-hand side is going eastward. But look at Mercury, what Mercury is doing now. Mercury is reversing its direction. It's going now for a few days towards west. This apparent motion of stars, of planets, and the sun and the moon in respect to the stars in the background. This apparent motion is called prograde motion. So prograde motion is the eastward motion of planets and the sun. This is going to be in your exam, so better make sure you take notes. So the prograde motion is the apparent motion of planets and the sun in respect to the background stars, and is always towards east. But sometimes these planets, they change direction and they move westward. And we call this changes a retrograde motion. So retrograde motion is the apparent motion of certain planets, and in fact all planets retrograde for a few days in respect to the background stars. So the second type of apparent motion is caused by Earth itself revolving around the sun. So as the sun moves back towards the eastern sky, exactly what is happening is Earth is going and revolving around the sun. I'm hearing a microphone in the background. If you could mute yourself, that would be great. If you could mute, that would be great. But that's the second type of motion. Can you guys hear a background? Can you please mute your microphone?
Can you hear me?
I can hear you, but there is a noise in the background.
No, not in my house.
Now it's gone. So let's go quickly through the slides in that we have at Canvas. Celestial sphere, again, it really doesn't exist, but is a nice way to represent our sky. So let's take these two views at the same time. The view of somebody that is outside, that is not spinning along with Earth, and the view of somebody that happened to be sitting on Earth, which happened in the right-hand side. So here's the animation going. And Earth in the left-hand side, Earth is spinning on its axis of rotation. And what I'm going to do, I'm going to put some stars in it. I'm going to put Orion, and I'm going to put the Big Dipper in the sky. And some stars just for fun. So look at this. The stars, they move. As I mentioned in the beginning, the stars, they move, but they are so far away, we really do not detect their apparent motion. And so Earth is spinning, and on an hourly basis, what we observe, what we perceive, is stars or group of stars apparently rising in the eastern sky and setting in the western sky. So this apparent motion, again, is not caused by a celestial sphere carrying and dragging the stars in the sky, but it's caused by our spinning in the space. Basically, that's what we do. Any questions so far? Is all good?
Sounds about right.
Okay. Now let me bring another subject now to your consideration, and that is the moon's phase. That is an important also cycle that we perceive in the sky. Let me bring my tablet. Just a second, I will be back. All right. Take a simulation here. That is the lunar phase simulator. So let's consider one part of the sky where the sun is. And here's Earth, is the moon, and Earth is pretty much showing in such a way that we are standing in the north celestial pole looking down on the orbital motion of Earth around the sun. That is the one that is going to be shown here. So this whitish dot in the center of Earth is North Pole, basically. And these little people here happen to be sitting in the equator. So there is no tilt of Earth axis of rotation. This is a simulation just to make it think simple. but it will help you to visualize and understand the moon's phases. So in the right-hand side, you have a window with the moon in the sky as it appears in this particular phase. And in the third window, which is down below here, it shows the person and the relative position in the sky of sun and moon. So the first thing that I will do is to do something that astronomically is not possible. I will stop Earth spinning. So Earth is not going to be spinning anymore. And what I will do, I'm going to move the moon around Earth, because moon orbits Earth and it takes 27.3 days. Is the so-called sidereal lunar month, right? Sidereal has to do with the stars in the far background. Is the time that takes the moon to complete a true orbital motion around the Earth. Is not the time it takes the moon to complete a sequence of phases, let's say going from new moon to new moon again. This is 29.5 days. It's called synodic month. So the sidereal month is the true orbital period of moon around Earth. And the synodic month is the period of phases, 29.5 days. So in olden days, they would say, okay, see you in 2 months, which means I see you in 2 times 29.5 is about 59 or 60 days or so. Okay, so each month, 30 days, the word month has to do with the moon, this period of phase. In 27.3 days, it was more difficult to determine just by observing the moon thousands of years ago, but it was eventually known with precision. So what I'm going to do, I'm not going to rotate Earth, and I'm going to allow the moon go around Earth and see how the phases develop in this window over here. So now the moon is in a crescent phase, and when the moon gets to the first quarter right here, there is a very nice 90 degrees angle relating moon, Earth, and the sun. So we have a 90 degrees angle right here, and that's why we see the moon as 1/4. In a circumference, a quarter of a circumference is 90 degrees angle. And if we take another sequence of phase, the moon is going to be in the furthest position of Earth in respect to the sun, and then we call that phase full phase. And then we go through the gibbous phase to the last or third quarter, and then we go through the crescent phase again. So see, this crescent phase, as we see in the sky, is different from this crescent phase as we see in the sky. So the sequence of phases that goes from new moon to full moon, they are called waxing phases. So the moon is waxing because the moon apparently is growing in its brightness. It starts, sorry, I'm going backward here. So it starts as a new phase, and then go to the waxing crescent phase, and then it goes to the first quarter, waxing gibbous moon, full moon, and then it starts a sequence called waning. Waning is growing smaller. So it's starting out with waning gibbous phase, last quarter, and waning crescent phase, and then eventually the moon is back to the new phase. Now, when this happens, I mentioned the moon takes 27.5 days to complete a whole sequence, or if you go from new moon to new moon, it's 29.5 days, which means during the time the moon is going around Earth, in 29.5 days, Earth has rotated, has spin also 29 or so days. So let's see how the whole animation works. So you see in the sky, the moon appears to be, as we observe sitting on Earth, the moon appears to be departing and going away from the sun as the sequence of phases progress. Now we are in the first quarter. Let me pause animation now. In the first quarter, let me go back here. Right there. Right. In the first quarter, at this position here, we see the sun rising, but we don't see the moon. And we will start to see this moon rising. Let's see the tip of the moon right there at about noon. See, this time of the day is noon. Let me bring time and angle. 90 degrees. Let's take the angle away. So noon. Now at 6 p.m. in that phase, at 6 p.m., the moon, first quarter, is high up in the sky for an observer on Earth. And the moon first quarter goes setting. Remember the rise and set? It sets at midnight for an observer. So you are the observer, you look west and see the little moon setting there. A few hours later, so if you put 1 hour later, the moon is down. You can't see the moon anymore, although the moon is still first quarter. So this simulation, the link exists in our Canvas course. And I really suggest you to explore if you want to learn more about it. So you have any question regarding this simulation? It's all good. It's it's difficult because you have three things happening at the same time. And we are not used to the fact that Earth is not a flat thing. Earth is a sphere, and we happen to be in that sphere. Okay. The last thing I would like to show you is a little tricky thing that you can do to figure out at what time of the day any moon phase is supposed to rise or set. Remember, rising and set is the time the moon goes from below horizon to above horizon. This is the rising moment. And when the moon goes from above horizon to below horizon, we call the setting time. So rising and setting time. So let me try to go over that part. Let me open a page here so I can work on it. I think I was here. Okay, I think I can annotate now. So first, you have to determine from which direction the sun the sun rays are coming from. So this is pretty much the sun. So you can test yourself, you can do yourself that way. And from that perspective, you are pretty much sitting on the north part of the sky. You bring Earth right here. And right in the center is North Pole. North Pole. And the circumference is equator. So if you want to give the time of the day to somebody standing on the equator, so somebody standing here, that is a noon. Somebody standing here, what time of the day that is, assuming Earth rotates counterclockwise, assuming Earth rotates from west to east in the sky, what time of the day this should be? 6 p.m. Now 6 hours later, this person is going to be dragged to this position, and that is midnight. Midnight. And you can kind of see that happening because Earth is in the way of the sun. So you are pretty much in the Earth's shadows if you happen to be right here, midnight. And then 6 hours later, more or less, that person is going to be here, 6 a.m., 6 a.m. That person looks east and see the sunrise right there. That's the sun rising. And look west and see stars. So stars are there. Okay? Now let's place the moon. You must know where the new moon should be in this diagram. So the new moon should be right here in this diagram. That's the new moon. New moon. And the new moon is the first phase in a sequence of phases we call waxing. So the waxing sequence of phase going from new all the way to the full moon. And the full moon happened to be the furthest position in respect to the sun, as Earth orbits the sun. Now, let's call this the waxing phases. Waxing phases. Now, any phase in which the moon is between the sun and Earth, they are called crescent phases. Crescent phases. In any phase the moon is that is between Earth and that full moon, they are called gibbous phase. Gibbous phases. So gibbous phase and crescent phases. And when you have a perfect 90 degrees angle is the quarter phases. So basically, when the moon happens to be in this position, this phase is a waxing crescent phase. When the moon happens to be here in its orbit, this phase is waxing gibbous phase. Waxing gibbous phase. And then it goes to, oops, too many S's. And then it goes to the full moon, and then the sequence of phases from full moon all the way to the new moon are called waning phases. Waning phases. Waning phases. And so the phase right here would be a waning, gibbous phase, and any phase right here you would call waning what? Crescent phase. Crescent phases. All right. So let's say you can make sense of this. You can understand and reproduce this at home. Is a nice way to, if somebody tells you, okay, which moon's phase that is, you can, in a little sketch, you can place the moon in it. You must know what the waxing phases are. You must know the moon goes around Earth in a counterclockwise direction as you look down on it from north, the same way Earth rotates on its axis in a counterclockwise direction. Okay. Now, what I'm going to do next is, okay, if I give you one phase, at what time of the day is that moon rising and what time of the day is that moon setting. So for that, let me see if I erase all of that. I think I can erase. Can I erase all of it? Should have an easy way to erase everything, huh? View, tools. No, that's for the file. I think I have to erase like that. No, that's gonna be too bad. Oh, okay, I can use down here, no problem. So bring the sun again, and Earth, North Pole. You need to know the exact time of the day. So this position here represents what? Noon. The clock here is what? 6 p.m. Because Earth rotates like that. If somebody is at noon at this part of Earth, 6 hours later, Earth rotates and brings that person here. And here would be midnight, and up here would be 6 a.m. So you should be able to do that. The next thing you do is a circle that would represent the moon around orbiting Earth. A nice circle, not mine. And then somebody should provide you with a moon phase. So Eduardo, why don't you give me a moon phase, any moon phase you want?
A new moon.
A new moon. So what you do, you have to know where to place the new moon in this case. So the new moon is the phase that lies between Earth and the Sun. We just had an eclipse. It's a cool eclipse, and that's the new phase. So what you do next is the letter T. You take the center of where the moon is, draw a line to the center of Earth, and make a T, like this. So 6 p.m. and 6 a.m. represents 6 a.m., the time this moon is rising. So the new moon rises at 6 a.m., in fact, together with the sun, and this new moon sets at 6 p.m., also the same time the sun is setting. Okay? So it's a tricky thing. You just draw a line and do a T. Right. And then you can determine rising and setting. So give me another phase. More complicated. Miguel, shoot it. Any phase you want. And then the question is, at what time this phase is supposed to rise or set?
About the waxing phase.
Waxing phase, which one? Gibbous or crescent?
I'll choose gibbous.
Gibbous. So you should know this is new phase. This phase here is the full phase. And the waxing are the phases from new to full. So waxing should be somewhere here. If it's gibbous, should be there. What do you do next? A T.
Interesting.
So here is the rising time. Here's the setting time. Now, what time this is?
Could be my next question.
Is what? 3 p.m.? And this is about 3 a.m. So the gibbous, I mean, depend on which gibbous phase it is, but let's say I'm choosing the middle of the gibbous phase, waxing phase. So that is going to give us the moon rising at 3 p.m. in the afternoon and setting at 3 a.m. Now, if I go to the software we just learned, not this one, the Starry Night. Let me see what it is. There you go. So let's see if I can catch moon phase somewhere here. That's Scorpio over there, and let's increase. Let me see this one. Okay. So where's the moon?
Right there.
Oh, the moon is right there. Okay, look at this phase over here in the sky. In fact, let me bring the daylight again. That's the sun, and here's the moon. In fact, let me take 3 days before. Let's see, 11. It's easy to see the moon. So January 11, see the moon over here? This phase is one that is crescent, right? And to make it simple, let me get away from the daylight. So it's a crescent phase because more, if you look at the moon closer, so only a tiny part of it is being lit by the sun. So it's a crescent phase, right? And so at what time of the day is this moon rising and set? So we go to our diagram. Where is it? It's right here. We go to our diagram. It's a waning crescent phase. Waning or the phase is somewhere here. So we would put it somewhere in there. And we draw our T. Oh, look at this. It's going to be rising at 3 a.m. and setting at 3 p.m. Rising 3 a.m., setting 3 p.m. Then we go back to our little simulator. And, well, it's not so bad, right? Given the approximation, 3 p.m. is a good thing. So the moon set at about 3 p.m. And at what time is the moon rising? So please, I'm going to move the sky backward. This is not real. I should never do that, but I'm kind of a lazy. And I'm turning the time backward. We can't do that in classical physics. So that's the time this moon is rising. It's about, 4 a.m. or so. So it's not bad. So if you want to impress somebody looking at the moon in the sky, first thing you should be able to identify which phase it is. The waning phases, as it's shown in this picture here, the waning phases, the bright part of the moon is to the east part because the sun is chasing the moon in the sky. Those of you who like Star Trek, The Next Generation, there was a show. There was a civilization that communicated by myth. And they found an archive. And there was a myth of the sun and the moon as gods. And in the waning phase, the sun is chasing the moon in the sky, as you can see here. It does, right? So that's a waning phase. And the bright part of the moon faces the sun. In the waxing phase is different. So in the waxing phase, let's go fix this time here, but go 14 days ahead. Let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's enough. So now we went several days ahead, and now we have a moon that is waxing. See? And in a waxing phase, the moon chases the sun in the sky. So you have the moon as a predator, and the sun is a prey that is being chased by the moon. And the moon is a waxing with the bright part facing west, or the bright part facing the sun. If you wait a few more days, if you go a few more days, and that's what I'm gonna do. See, January 23. I go 1 day, 2 days, 3 days, 4 days, 5 days. Now this is pretty much a gibbous moon. The gibbous moon is rising in the late afternoon while the sun is setting. So they are moving apart, as we saw in that diagram. All right? Any question on that one?
Interesting concept.
Yeah. So it's a cookie recipe that might help you in some exercise. Instead of memorizing a bunch of things, you just use a simple concept and you get it done.
Yeah, it makes a lot of sense the way you actually explained it. So that was very helpful.
Okay, very good. All right. So for the Astro Lab people, see you guys mañana, hopefully in the observatory if the weather is good. I will make sure that is the case.
So, Professor, on the first part, and going back, I know because I kind of got here late to the meeting itself. I was having internet problems, so I had to get online with internet with the Comcast to help me try to get this squared out. That's why I kind of entered the class late.
Okay, no problem. No problem.
Finally able to get it up. So what I
had the problems on my own. I started 10 minutes late because I didn't have Flash and I couldn't run some of the simulations.
Right, and so and another thing on that app that you wanted us to download.
Oh yes, Stellarium. Yes.
Yes, Stellaria. So I had this. I downloaded Stellaria on my phone because it would not accept it on my Mac because it said it. Yeah, it said that mine was it was out of date. It had to be higher than an OS 10.
Oh, I see.
For me to install it, so it would not allow me to install it into my Mac.
So were you able to put it in?
I installed it in my iPhone.
Oh, your iPhone, and probably you had to pay something.
Yeah, but it is what it is. And I mean, it was part of kind of the prerequisite that you were asking for, so I just went ahead and paid for it because I couldn't do it. I couldn't do it on my laptop. It wouldn't allow me.
So how much did you pay for it?
Open the download that I did.
Yeah.
And it told me that my computer didn't meet the specs for.
Oh, okay. How much did you pay for it?
$3.
Oh, okay, that's not bad.
It's not bad.
Yeah, it's a coffee.
Yeah.
All right.
So I just went ahead and got it, but I got it on my phone.
I'm gonna make coffee for the students in Astro 10L, so then I will pay you back.
No worries, Professor. I just want to let you know what I had to do.
Okay.
But so my question to you was: I know since you started like 10 minutes late, was there something that I missed for the first part?
No. I start directly talking about daily or diurnal motion, which is this type of motion here.
Oh, okay.
Stars rise in the east and set in the west.
Okay.
And you are in the lab class, and tomorrow that's what I would like to explore, but with the telescope. Okay.
Okay.
All right. Sounds good.
All right, Professor.
Okay.
So
I'm stopping the taping now. I'm not taping right now.